how to say? Okay, people, I need your understanding. Some parts will look like your secondary school knowledge, and you will be very inclined to switch off. Can I urge you, can you please don't? In secondary school, a lot of things you memorize. For example, for brine, you will just memorize that chloride concentration high, whatever happens. Here, once you are doing A-levels, you need to learn to use data to explain. I'm going to use simple examples to show you, which is like sodium chloride, that kind of things. You are going to face questions that are slightly more challenging. Okay, so drawing data, how to use data to explain something I need you to learn from me. I know it's boring. Okay, I know it's boring. Trust me, I'm the one talking. Okay, now next thing is this. This topic, I think Ms. Ma will say the same thing to you. One of the hardest things about this topic is finding the correct data. It's very hard to find correct data. You look through this set of notes, it'll be very easy because I found the data for you. I wrote everything down for you. One of the hardest data to find is anything that involves. One of the hardest electrochemical data to find is anything that involves. Anything that involves. Okay, people start to you should start doing your electrochem tutorial. Water. Anything that involves water. There are a lot of equations involving water. Okay, so please learn. Let's try and follow. Okay, there are some concepts that are similar to Electrochem I. Some concepts that are slightly different. Not that they are different, but the perspective is different. So in order for me to start, let me just recap some things from Electrochem I so that we are on the same page. Okay? Okay, people try and follow me. So Ms. Ma, what she taught you all in Electrochem I is this. She taught you about voltaic cells. A voltaic cell is basically a battery. On my slide here is a very specific type of ancient battery. It's called a Daniell cell. Don't have to remember names, okay? I'm just using an example so that I can discuss with you. This is a Daniell cell. A Daniell cell is a kind of battery. It is a kind of voltaic cell. The interesting thing about it is on the left side, you have a zinc sulfate half cell. On the right side, you have a copper sulfate half cell, linked together by a salt bridge, connected to external circuit to, sorry, I know there are SO3 classes here. I don't know what you all learn nowadays. What's this? Light bulb, thank you. It's a light bulb. It's not X-Men logo. Okay? It's a light bulb, so I need you to learn some, take note of this. How do I know that, because this is a battery, right? How will I know how the electrons flow? You need to look at the electrochemical data, right? So when you take note of the species involved in each half cell, you can deduce that I need to call up these two electrochemical data, and you will start comparing their values. People, okay? You should realize you don't have much time. Whatever nagging that I'm doing on you, treat it as helping you to revise. Okay, please do that. Okay, try and think along with me. Okay, don't waste your time here. You are here for a reason, right? You have to sit here, right? You might as well do something productive. Okay? Okay, so we're going to look at these two relative values. What I've deduced is that the copper half equation is more positive. Right? A more positive E0 tells me that its equilibrium position lies somewhat to the right. Agree? And that is why it being the more positive E0 value, I understand that it will undergo reduction. The other one being a less positive value, in fact it's negative, will undergo oxidation. Based on this, I can actually write an overall equation that looks like this. Okay? Now, is this reaction spontaneous? Is this reaction spontaneous? Does it happen on its own? It does. Okay, before that, it's spontaneous in the sense that electrons will flow, yes? How do you decide where the electrons will how the electrons will flow through the external circuit? Do you all know? Make a guess, not make a guess, make a deduction. Will your electrons flow from left to right or right to left? Left to right, very good, thank you for your responses. Okay, it's going to be left to right because, because if you look at this half equation here, you realize that because I already told you it will proceed backwards, meaning zinc will give out electrons. If zinc gives out electrons, you know that the zinc electrode is the one that electrons will come out of. That's why electrons move from left to right. And because of that, my battery will light up. My light bulb will light up. Okay, battery lighting up is actually quite a scary thing. Okay, my light bulb will light up. Okay, next thing is I can calculate a E0 cell, right? I can calculate E0 cell by using E0 cathode minus E0 anode. I will get 1.1 volts This number, for you now, it may not seem relevant. I want to do a discussion on this number later, so just bear this in mind. How do you prove that it is spontaneous? What do we use as a gauge of spontaneity of a reaction? What do we use as a gauge of spontaneity of a reaction? Delta G, okay? Actually, delta G naught, right? So towards the middle of the previous topic, you were introduced to this equation. Delta G naught equals to NF E naught, right? N and F are positive. E naught in this case is positive. Therefore, delta G naught, because of this negative sign, is negative. That's how you know the reaction is spontaneous. Okay, people, the links between the topics, please know them well. And just to remind you, this is acting as a battery. Now, because it acts as a battery, you will realize something. As the light bulb shines, certain things will happen, right? You will realize that your zinc electrode will get smaller and smaller. Your zinc concentration, zinc 2+ concentration will increase. Copper electrode will get larger. Copper sulfate concentration will start to decrease. And what you will see is this. Okay, people, just look at the thing, look at the screen. Okay, the size changes, right? The color of the solution will also change. Okay, I don't want to push it too far. Can you see that you're actually draining your battery? Just like what your phone is doing now. You are draining your battery, right? Can you tell me when your battery, for example, in this case, will go flat? Anyone shout out one proper answer? You're like my conscience talking to me. They're all murmuring. Anyone? Give me one definite, one, just shout out one. How do I, like my battery is completely depleted. Means what, for example? Shall we focus on the copper half cell? Maybe focus on the copper half cell. If my battery is completely depleted, so what could have possibly happened to my copper half cell? Sorry? Okay, never mind, I heard something. Copper 2+ concentration, right? The copper 2+ concentration dropped until very low. It could be that there's no copper left, no copper 2+ left, for example, right? It's a possibility. Another possibility would be my zinc electrode completely gone. Possible, right? Okay, but let's not push it to the extreme, okay? Let's stop here. Let's stop at this stage. Now, my question to you now is this. Will the reverse reaction happen? Meaning, can I get the electrons to flow from right to left? Can I get it to do that? Will it happen by itself? No. Okay, good. Good that you can intuitively tell me no. Okay, just to clarify, the reverse reaction, basically what happens is I swap the reactants and product side. Okay, reverse reaction meaning just swap the reactants products. Okay, what happened? Oh, okay, sorry. Okay, so for the reverse reaction, can you see my E naught cell is now negative? If with a negative E naught cell, I can deduce that delta G naught is positive, and that is why the reaction is not spontaneous. Okay, people, can you tell me what do you understand by the term non-spontaneous? The reaction, will it happen? Will it happen? No? Okay, I heard a very resounding no from my left side, thanks. It's not that it will not happen, okay? It cannot happen on its own. Okay, delta G not being positive doesn't mean it cannot happen. It just cannot happen on its own. So you need to supply energy to help it happen. Okay, and how do I supply electrical energy? Battery, thank you. Battery, the first affirmative answer I got today, a battery. Okay, and because I want to do that, I want my battery to flow. I want my electrons to flow a particular way. I have to place my battery properly. So let me just define the battery properly for some of you. You may not know what a battery looks like on paper. Okay, so this is the symbol for a battery. The short vertical line is the negative terminal. The long line is the positive terminal. For a battery, it forces electrons to come out of its negative end. A battery forces electrons to come out of its negative end. So this is my intention. This is correct. Agree? Now, so because I supply energy to make the reverse reaction happen, this is actual. Sorry, do you all see that? Okay, if you didn't see that, good. Okay, people, can I just ask you, can you roughly estimate what is the voltage I need for my battery? Okay, sorry. So some of you evidently saw that next click already. But can you understand why intuitively? Because here the E0 cell is negative 1.1 volt, correct? So if I want to force the reaction to happen, even though it won't, I need to supply more than 1.1 volts. Does that make sense? Makes sense, right? Okay. And what happens when I supply more than 1.1 volt? Look at the diagram, please. As I supply more than 1.1 volt, my copper electrode gets smaller, my zinc electrode gets bigger, correct? My copper 2+ concentration starts going up also, yes? Okay, this is actually the basis of electrolysis. Okay, this is the basis of electrolysis. You are using an external source of electrical energy to drive non-spontaneous chemical reactions. Okay, meaning the reaction actually does not want to, the reaction will not does not happen by itself. You are helping it happen, okay? Now this one may drain your brain power a bit. I want to see whether you noticed something. If you cannot get this slide, never mind, just forget it, okay? Now this is what I started the lecture with. A battery making the bulb shine bright. As the reaction proceeds, you realize that I'm starting to deplete my battery. The bulb still shines, but you notice certain things about my electrode, you notice certain things about the color of my solutions. I took a commercial break, and I asked you, can I force the reverse reaction to happen? Yes, I can by putting a battery there. And I show you what happens if I let the battery run for a while. Okay? People, can you tell me what's happening here? The green arrow. Do you notice what's happening here? Top right-hand corner, that is my depleted battery. Top right-hand corner, that's my depleted battery. What did I do to my depleted battery? I connect it to an external power source, right? Then I let the external power source do its job. Then come here. It becomes, this battery looks like original, right? This battery now looks like original, right? So what did I do? What did my green arrow achieve? Charging. I charged my battery. Okay? I actually ended up charging my battery, which is what you will do when you go home tonight, right? Or some of you are charging your batteries now already. Okay? I'm actually charging my battery here. Okay, so just re-emphasize this part. In principle, I am recharging my battery. But unfortunately, I hope you learned this from Electrochem I, not all batteries can be recharged. Okay? Daniel cell, the one that I'm showing you, is actually one of the batteries that cannot be recharged. And you can understand why after I teach you the 4 factors today. You can understand why not all batteries can be recharged after I go through the 4 factors with you today. Okay, I'll leave this as open-ended question. You go back, think about it. Okay, so let me do a quick introduction before I go through the 4 factors. Okay, so initially, past few lectures, you are doing voltaic cell. There's a spontaneous redox reaction that provides electrical energy. What I'm going to focus on for the next 1.5 lectures is electrolytic cell, where I need to supply electrical energy to force something that is non-spontaneous happen. I'm going to force a non-spontaneous redox reaction happen. So if I were to formally define electrolysis for you, it is the process of passing electricity from an external source to force a non-spontaneous redox reaction to happen. Okay, so for every electrolytic cell, you will notice this, there is a battery. Okay, there will be a battery here. I've taught you how to read a battery in case you don't understand the symbol. The short vertical line is the negative terminal. The longer vertical line is the positive terminal. There's always an electrolyte as well, which can be molten or aqueous. Now, you realize that for a previous topic, right, a salt bridge is a very common feature, right? For a voltaic cell, you will tend to see a salt bridge. For this one, you tend not to see a salt bridge, okay? But there are examples where a salt bridge is present, okay? Lastly, there will be some electrodes. And what we need to decide is actually which electrode is the cathode, which electrode is the anode. How do we go about doing that? You work from the battery, okay? You work from the battery. The battery is the motivator. It drives the reaction, okay? Okay, so the negative end of the battery will always push electrons out. The negative end of the battery will always push electrons out to the right side. Electrode, in this case, it is the blue color electrode. Electrons flow here. So any chemical species in the surrounding of the electrode can take electrons from the electrode. Make sense? Because my battery drives electrons to the electrode, chemical species around the electrode can actually gain electrons from this electrode. The moment it gains electrons, my chemical species gain electrons, what happens? Reduction happens. And because reduction happens, by definition, we call this the cathode. Reduction, cathode. This is a definite relationship and it is fixed. It is by definition. Okay? You will not have any ambiguity about this idea. Reduction is always happen at the cathode. Let's look at the next one. Let's look at the left side electrode, the green electrode. A battery will always draw electrons from this side, from the green electrode, okay, because of the positive end. So electrons flow from this electrode. Where is the electrode going to get electrons from? It's going to get electrons from chemical species which loses electrons. Okay, as it loses electrons, the chemical species loses electrons, oxidation happens. And because oxidation happens here, I know for sure this is called the anode. Okay, so anode oxidation, cathode reduction. This you should know very well. Okay? Now, as electrolysis progresses, you will realize there are certain changes. Okay, this part is not too difficult. I'm sure you know it. There are some chemical changes. The chemical changes, because of redox reactions, they're happening either to the electrolyte or the electrode. Now, because of the chemical changes that happens within the cell at a very microscopic level, right, it will cause physical changes that you can see. For example, evolution of gas, color changing of electrolyte, and of course your electrode changing size, which is one of the examples I was talking about just now when I showed you the Daniell cell, right? Okay, before I move on, can I just get you to take note of some terminologies? We're going to use this term a lot, liberated and discharged. When I say a species is liberated, it means that it undergoes either reduction or oxidation. Okay, the same for discharge. When I say something is discharged, it underwent oxidation or reduction. And just take note, this is bottom of page 2, this relationship holds. Okay, this relationship is always true. Oxidation, anode, cathode is reduction. Okay, this relationship is always true, which is something you can notice in this summary page I gave you, page 3. Okay, I've actually put the voltaic cell and electrolytic cell side by side for you to compare and contrast and realize the difference. Now, in order for you to do a question on it, one of the first things you must do is you must identify what cell it is, okay? What is the most obvious way to identify which cell it is? You can identify one cell very easily. If that feature is not there, it's probably some other cell. Battery, okay? You are looking for the battery. Once there's the battery or external source of energy, okay, it will be an electrolytic cell. And therefore, that's why I highlighted that one in purple for you. That is a very distinguishing feature for me. Okay? Next thing I want you to take note, anode undergoes oxidation. For both voltaic cell and electrochemical cell, oxidation happens at the anode because it is true by definition. But please take note, you might want to highlight the one at the bottom there. Do you realize that polarity is different? The polarity is actually different. I suggest you don't memorize this. You can actually derive this in your head. So let's try this for voltaic cell, okay? Anode, oxidation happens, right? At the anode, oxidation happens. Oxidation means that my species are giving out electrons, correct? So electrons are going to flow out. Electrons are going to flow out of this electrode. And that is why this is the negative terminal. Okay, this is the voltaic cell I'm talking about. Okay, let's do the same for the cathode. Cathode is always reduction if you compare. Cathode is always reduction, but you realize that the polarities are different once again. Okay, this time I'm going to use the electrolytic cell as an example of how to think about it. In an electrolytic cell, the polarity is determined by the battery. In an electrolytic cell, the polarity is determined by the battery simply because when the negative end of the battery will push electrons out to this particular electrode. That's why it's negative, because electrons arrive there. Okay? Now, when I do electrolysis, when I pass current or electrons through the setup, not all my species will come out at the same time. Okay, please take note, not all of them will come out at the same time. Some will come out first, some will come out later, and what affects that is the one that comes out first is the one that requires the least energy. And I hope this makes sense to you. Okay, because a battery drives the reaction. You need to supply electrical energy. So the most likely one to happen is probably the one that requires the least energy. Okay? And that's why we call this selective discharge. There are 4 things that you need to consider. There are 4 things you need to consider before you can decide what's going to happen. Okay, I'm going to start with the most simple case. I'm going to work up the difficulty level. But again, as I said earlier, people, I need your understanding. Everything here, yes, you have seen in secondary school, but I need you to take a different perspective because I need you to incorporate E0 value in your discussion. Okay? Okay, the first example I'm going to start with is molten sodium chloride. Okay, I will compare molten sodium chloride with aqueous sodium chloride later, but let's start with molten. While I run through the factors, I'm also going to do something else. I'm going to try and help you be more systematic, okay? Let's analyze the situation and understand what I'm dealing with. First, I will always tend to identify the species in my electrolyte. Okay, in this case, because it's molten sodium chloride, it's just sodium plus liquid and chloride liquid. Next, I will identify the type of electrodes present. In this case, these are inert electrodes, meaning the electrodes will not react. Okay, the electrodes will not react. So it's actually quite a simple case. Now, for the cathode, how do I figure out what happens? So let's call up the diagram. Okay, you don't always need to do this. Okay, so let's do the train of thought. Electron flow from the negative end of the battery to this particular electrode. This is the negative electrode. Okay, and therefore, you will realize that my cation ions are actually attracted there. My cation ions will tend to go to the negative electrode. Now, in secondary school, you may have been taught this, and this only works for electrolysis, by the way. Cation ions go to the cathode. Okay? In this case, cation ions go to cathode because for electrolytic cell, the cathode is actually negatively charged. But can I get you to be very careful? Although that statement is very convenient, it doesn't hold true all the time. It is convenient, but it doesn't hold true all the time. We have seen examples where an anion will actually go to the cathode. You might want to think about why, okay? But anyway, next, the other electrode will be positive, and therefore my anion will go to the anode. Okay, my anion will go to the anode, and therefore I can predict what will happen there because there's not much choice. There's not much choice as to what will happen. So as I said earlier, sodium plus goes to cathode, it undergoes reduction. Sodium plus goes to cathode, undergoes reduction. Chloride goes to the anode and undergoes oxidation. Okay, this one you don't really need your data booklet to do so, and I can actually write an overall equation for it. People, is there a ringing sound? Is there a ringing sound? Okay. Justin, you watch out, are you? Okay. Anyway, thanks. Sorry, because I keep hearing this wong, wong, wong sound in my head. Okay. Shh. Okay, calm down. Sorry. Shh. Because it's very distracting for me. Shh. Okay, as the reduction or oxidation proceeds, right, what you realize is you are going to start producing liquid sodium. You produce liquid sodium because the temperatures are very high, by the way, so the sodium produced will actually melt into a liquid, okay? And you will realize on the anode, you will see chlorine gas being produced. Okay, so this is the simple case, molten sodium chloride with inert electrodes. Okay, next, let's talk about aqueous. Once I have aqueous, things are going to start getting a bit more complicated. First, I will realize that sodium plus, there's chloride as well, and there is water. There's sodium plus, there's chloride, there is water present. Please don't ignore the water. Next is still graphite electrodes, which are inert. Okay, let's come back to this diagram. We already established what happens at cathode and anode, right? The sodium plus will get reduced at the cathode. But please be careful. because of water being present everywhere, it is very likely for water to be reduced as well. It's very likely for water to be reduced as well. So you must think about, will water be reduced or will sodium plus be reduced? And how do I go about deciding that? Next, at anode, just now we already established oxidation of Cl minus happens, but because there's water everywhere as well, you need to consider whether water will be oxidized as well. And how am I going to make that decision? This leads me to my second factor. Okay, this leads me to the second factor, and this is the rule of thumb. If you analyze and you realize that more than one species can be discharged, you need to compare their E naught value. So you need to compare their reduction potentials. Okay, so let's look at this. Just remind you, at the cathode, it's either sodium or water. Okay, people, I'll go through this example a bit slower because you need to find the correct data from your data booklet. Okay, and most of the time, the first time you do it, you will end up finding the wrong data. Okay, because in the cathode, reduction happens. At the cathode, reduction happens, and at the cathode, reduction happens, and the data in your data booklet is written in reduction form, right? Your data booklet from left to right, the equations are written in reduction form. I'm going to look for sodium and water on the left side of the equation. Okay, I'm going to look for sodium and water on the left side of the equation. So can you please take note, I actually highlighted certain things for you, okay? I'm going to look for them on the left side of the equation because I know it will undergo oxidation, undergo reduction. It will undergo reduction. Now that I have these two E naught values, how am I going to decide which one undergoes reduction? So remember this, a more positive E naught tells you that the equilibrium position lies to the right. Correct? A more positive E naught value tells you equilibrium position actually lies more to the right, so it has a greater tendency for reduction. Based on that thought, I'm going to look for the more positive E naught value, which in this case is the one that involves water, which is why I know that reduction of water happens. Okay, so let me just go through phrasing with you once. Because the E naught involving the reduction of water is more positive, or in this case I said less negative, it has people learn this phrasing please, it has a greater tendency to be reduced. Okay, another thing I want you to take note is this. From the data booklet, when I quote data from the data booklet and I quote the equation, I quote as what I see in the data booklet, which is all the data given to you involve equilibrium arrows, right? But look at what happened at the bottom here. I've already found out, I've already decided what's going to happen. At the cathode, the reduction of water is going to happen, so please change it to a full arrow. Okay, please take note, don't lose marks for nothing. Okay, when you code data, you might find that, okay, because the data booklet shows you equilibrium arrows, you will copy the equilibrium arrows. But once you have decided what is going to happen, please show the full arrow so that you know it is the one that's going to happen. Okay, what about anode? At the anode, oxidation happens. It's either the oxidation of chloride or water, as we have previously talked about. So if I go to the data booklet, do you know where to look? You are going to look for chloride. You're going to look for equations with chloride and water on which side of the equation? Right side. Okay, you are going to look for chloride or water on the right side of the equation, because going from right to left is oxidation. Okay, so I'm going to find these two values here. Okay, I'm going to find these two values here, and you realize that the species I'm interested are actually on the right. A less positive E naught value tells you there's a greater tendency for oxidation, meaning that a less positive value has a greater tendency for oxidation. Which one is less positive? The less positive one is the one involving water again, interestingly. And therefore, at the anode, water is oxidized. Please take note, look at my arrows again. Please take note how to phrase. Water has a greater tendency to be oxidized. How I know that? I look at the E naught values that I've used. Okay? Now, if I combine the equation, interestingly, you will realize it's actually the electrolysis of water. Okay? So this is my second factor that I've covered. Once I realized that more than one species can be oxidized or reduced at a particular electrode, you need to compare the E0 values. You need to look at your data booklet and call up the correct value. Okay, the next factor I'm going to talk about is concentrations. Okay, because you realize everything I did above, I'm using E0 value, meaning that, okay, but the thing is, E0 value is only valid under standard conditions. Can you just remind you what standard conditions are? 298 Kelvin, 1 bar, 1 mole per dm cube. These three tells you standard conditions, right? Now, once my concentration is not 1 mole per dm cube, these are non-standard conditions, and the position of equilibrium will be different now. The position of equilibrium will be different now, and therefore, E changes. Okay, for this topic, please be very careful about the terminologies that you use. I said E changes, I didn't say E0 changes. Okay, because E0 is defined under these conditions. E0 is fixed for these conditions. Once I'm out of these conditions, it is E. It is an electrode potential. Okay, it has no standard there. It is not a standard reduction potential anymore. It's just a reduction potential. So the example I'm going to use to illustrate this is, again, sodium chloride, but now I'm going to change concentration. I'm going to use concentrated sodium chloride. Okay, the analysis is the same. That's why I've shown everything again. But can I just get you to take note? Because it is concentrated sodium chloride, or we call it brine, the sodium plus and chloride concentrations are both very high. It is no longer at 1 mole per dm cube. It has a certain impact. Okay, let's do the easier one. I'm going to start with the anode. Previously, we predicted that the oxidation of water will happen. But let's look at this now again, because my chloride concentration is actually going to be quite high. Once my chloride concentration is high, this concentration goes up, my position of equilibrium shifts to the left. My position of equilibrium will start shifting to the left, and therefore it changes this value. It changes the value of the reduction potential. What will happen to the reduction potential value? Become more positive or less positive? More or less? People? If I increase my chloride concentration, equilibrium shifts to the left, my E value will become more positive or less positive? Less. Good. It becomes less positive. Now, it can become less positive such that, it is possible for the E value to become less positive and reach a smaller value, like, for example, 1 volt. Right? For example, only 1 volt. Now, what this tells you is now that because of the concentration change, right, now the E value for the chlorine-chloride half equation favors that oxidation. Okay? This oxidation, in fact, is now favored, which is why at higher concentrations you realize that the chloride is actually oxidized. Okay? This one okay? Now, if you look at the cathode situation is a bit more complicated. Yes, you are increasing sodium concentration. Because you are increasing sodium concentration, this equilibrium involving sodium will shift to the right. But, what this means is this value will become more positive. As it becomes more positive, it will become more positive, but the thing is, it is not possible to make it more positive than minus 0.83. I will make that value more positive, but it cannot become more positive than minus 0.83, which is why the reduction that happens at the cathode is still the reduction of water. Ken? Got it? Okay, never mind. When you do it yourself, I have one full example that's completely blank. When you do it yourself, then you experience the difficulty for yourself. Okay, let's move on to the next one. Nature of electrodes. Nature of electrodes. There are two kinds of electrodes you will deal with. Inert ones, typically you will use graphite or platinum if you want them to be inert. Basically, these do not participate in electrolysis, whereas reactive electrodes will participate, meaning there is one more thing you must consider when you are going to decide who undergoes oxidation or reduction. Okay? So I'm going to use the example of copper sulfate using copper electrodes. Now, copper electrode is considered a reactive electrode, and therefore, let's see what happens. Okay, at the cathode, cations are reduced there, so CO2 plus can be reduced there, or water, because this is an aqueous system. So I'm going to call up both equations involving reduction of CO2 plus or reduction of water. I'm going to look for the more positive one and decide that the more positive one will happen. Now let's look at the anode. At the anode, anions are oxidized there. Water can be oxidized there as well. One more thing now, your electrode also can be oxidized. Your electrode also can be oxidized. And therefore, you have to consider three possibilities. And because oxidation happens here, I'm going to look for the E0 value that is least positive, which is this one. It's the least positive E0 value, and therefore, I know that oxidation of copper happens here. Okay, I'm going to leave it to you to read what happens when I use an inert electrode on the copper sulfate solution. Okay? Okay, can you try this for me now? Give you 3 minutes. Try this for me. What to write in each space? Can you look at the other columns? They will help. Okay, I want you to experience finding data, looking for it, predicting observations. Can we try it now, please? Take out your data booklet. Take out your data booklet. Try it now. Prove to yourself, prove to me that you can do it. Okay, people, shh. Don't need to talk, just try on your own. Don't need to whine. Prove to yourself that you can do it. Prove to me you can do it. Give you about 3-4 minutes to try. Okay, all of you try. I don't care whether you're sleeping or not. Wake up, try. After you predict the reaction that happens, I want you to write down the observations, okay? Some of you are still finding data. It shouldn't take so long to find data. Okay, give you 1 more minute to finish this. Okay, to get some data, I'll give you time to finish this at home. Okay, from the noise level, I assume you are done. Okay? Shh. Now, I just want to show you what happens. I'll show you the answer next lecture, but let's show you what happens. People, do you know what this thing is called? Yes, this is the original YouTube. Okay? Spelled with a capital U. This is the original YouTube. Okay, from your perspective, you will see that the solution is slightly yellow, right? Okay, the solution, the solution is not supposed to be yellow. This is actually Ki with phenolphthalein in water. Anyone? Why is it yellow? Ki, phenolphthalein, water. Why is it yellow? I minus oxidized to I2 by oxygen in the air. By the way, whatever I just said, you can prove it with E0 values also. You can choose 2 half equations to prove that I minus can be oxidized by oxygen in the air. Okay, so let's see this guy do his thing. What he has done is he has used 2 graphite electrodes. Okay, I just want you to see whether your predictions are, your observations are the same. Okay, he will zoom. I can't zoom, he will zoom. Okay, can you see this? Can you see this? Okay, this is, okay, let's look at the other side. Can you see it's a bit cloudy on this side? What's happening here? What's all this? He's pointing it for me. He's a very nice guy. What's this cloudiness you are seeing? Okay, I just realized you can't see it very well. Oh, can you see the bubbling? Bubbling there, right? Okay, let's fast forward. What else do you see? Okay, do you get all those observations down? Effervescence. How come one of the electrodes turned pink? Right? Let's look at the other side. Sorry, let me fast forward a bit. Okay, I can't fast forward, sorry. Look at the right side. Do you see the bottom? Iodine, right? Okay, good. I'll show you the complete answers next lesson. Okay, Chem Reps, can you collect periodic table 2 and bring it along with you next lecture? We might get to start it. Okay, thank you very much.